Given what we've done so far, we can differentiate a bunch of functions. We can differentiate sums and differences and products. But what about quotients? Given a fraction, I'd like to be able to differentiate that fraction. I'd like to be able to differentiate a really complicated looking function like f of x equals 2x plus 1 divided by x squared plus 1, for instance. But we're stuck immediately because we don't have any way to differentiate quotients until now. Here's the quotient rule. So to state this really precisely, let's suppose I got two functions f and g, and then I define a new function that I'm just going to call h for now. H of x is this quotient, f of x over g of x. Now I also want to make sure that the denominator isn't 0 at the point a, so it makes sense to evaluate this function at the point a. And I want to assume that f and g are differentiable at the point a. I mean, I'm trying to understand how h changes, so I'm going to need to know how f and g change when the input wiggles a bit. Alright, so given all this setup, then I can tell you what the derivative of the quotient is. The derivative of the quotient at a is the denominator at a times the derivative of the numerator at a minus the numerator at a times the derivative of the denominator at a, all divided by the denominator at a squared. Let's use the quotient rule to differentiate the function that we saw earlier. So the function we were thinking about is f of x equals 2x plus 1 over x squared plus 1. I want to calculate the derivative of that with respect to x. Now the derivative of this quotient is given to us by the quotient rule. It's just the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. And it's all divided by the denominator squared. Now I've calculated the derivative of this quotient in terms of the derivatives of the numerator and denominator. So we can simplify this further. X squared plus 1 times the derivative of this sum is the sum of the derivatives. It's the derivative of 2x plus the derivative of 1 minus 2x plus 1 times, and again the derivative of a sum, so the derivative of x squared with respect to x plus the derivative of 1. And it's all divided by the denominator, the original denominator, squared. I can keep going. I've got x squared plus 1 times, what's the derivative of 2x? It's just 2. What's the derivative of this constant? 0. Minus 2x plus 1 times, what's the derivative of x squared? It's 2x. And what's the derivative of 1? It's the derivative of a constant. It's 0, all divided by x squared plus 1 squared. So this is the derivative of the original function that we're considering. There's no more differentiation to be done. And we did it using the quotient rule. So we've done a ton of work on differentiation so far. We can differentiate sums, differences, products, now quotients. What sorts of functions can we differentiate using all of these rules? Well, here's one big collection. If you've got a polynomial divided by a polynomial, these things are called rational functions. Sort of an analogy with rational numbers, which are integers over integers. A polynomial over a polynomial is, by analogy, being called a rational function. Now, since this is just the quotient of two things you can differentiate these rational functions. This is a huge class of functions that you can now differentiate. I encourage you to practice with the quotient rule. With some practice, you'll be able to differentiate any rational function that we can throw at you.